Okay, we're going to practice some C13 NMR. Right, so carbon 13 NMR, remember, tells us the number of different carbons. It's a lot simpler than HNMR. Right? There's no splitting, right? There's no integrations, but it does tell us the number of different carbons. It'll also, right, the frequency that it comes at, the frequency of the peak, tells us something about, right, what it's near. Right, that kind of that electronegativity, right? So it does tell us something about that. All right, so those are two things you can get from carbon NMR. Okay, so let's say you had this spectrum right here that I drew in. So the first thing you need to look at when you see a C13 NMR like this is essentially how many peaks are there, and that tells you how many carbons there are. Right, so how many peaks are there? How many peaks are there?
Like all time.
Total peaks. I see 1, 1, 2, 3, 4, 5, 6, 7, 8. 8. Okay. All right, we see 8. So that doesn't mean we have 8 carbons, does it? That means we have 8 different types. That's how many types we have, right? That's how many types we have. Okay. So without any other knowledge of this, right, you could look at this, like some things you should look for, and you'll have your access to your, right, tables and things like that. But I would look at this and you should say, that's for sure a carbonyl. That's the carbon of a carbonyl right there. Around 200, between 180 to 200, that's where the carbons of carbonyls end up. Right, it's really de-shielded, it's downfield. Right, this carbon's attached to an electronegative oxygen, so it's really de-shielded. Around here, this 160, 170 area, those are aromatic carbons. So they're coming from something like this, right? And I would probably even go as far as to say I know it's di-substituted, right? Because, right, this carbon and this carbon are different, but then these two are the same and these two are the same. That would give me 4 peaks in the aromatic region. Yep, follow along. And now these 3 guys down here, I mean, I kind of threw them in there. Like this might just be like a CH3 that's not really bonded to anything that's de-shielding, just like a methyl kind of by itself. And these, right, might be allylic or even, you know, next to O, right? Just kind of ideas, right? Without any more knowledge of this and that. And this is kind of what we're looking for analyzing these C13s.
What does de-shielded mean?
De-shielded means downfield. So if you're de-shielded, that means you're next to somebody that's pulling away electrons, right? Electrons can act like a shield from the radio waves, right? Remember in NMR, everybody gets lined up, and then the radio waves knock you over, and we measure, right, you coming back into the magnetic field, right? And so if you're shielded, that means you have a bunch of electrons around you shielding you from that radio wave. But if you're de-shielded, right, you feel the full brunt of that radio wave, right? To be de-shielded, you're next to somebody that's taking all the electrons. So if you're de-shielded, then we see you downfield, right? So if you look at this carbon, right, it's bonded to that electronegative oxygen, which is pulling all these electrons away. So this is very de-shielded, right? So that's why it's downfield. Okay, let's look at how to draw chair conformations. So let's take a 6-membered ring that looks flat, and we'll put a methyl here, put a chlorine there, put a ethyl there, and we'll put a bromine here. So what we need to do is take this and translate it into a chair. Right? So the first thing I would do is, right, you gotta draw a chair. Right, so my chair is drawn. Actually, I would take one step back and number the carbons in the other 6-membered ring, so I keep track of everything. 1, 2, 3, 4, 5, 6. Right, arbitrary numbering. So if you looked at this, right, the methyl, the ethyl, and the bromine are all cis to each other. They're all on the top face of the ring, right? And the chlorine's down. The biggest point of confusion is, can you be axial and be up? Can you be axial and be down? Can you be equatorial and be up? Can you be equatorial and be down? Yes, you can, right? So axial and equatorial have nothing to do with being up or down, right? So now I just make a choice. I say 1, 2, 3, 4, 5, 6. Right, the easiest thing to do now at this point, if I'd say 1 doesn't have anything on it, but I can draw in the H's at least for 1, right? I know this one needs to go up, axial, right? So if every carbon that has up axial, right, it has to have down equatorial. Down equatorial. Carbon 2 has down axial and has up equatorial. So what should be up though on carbon 2? Where do you want to put that methyl? That methyl's on carbon 2. I think it's just, you want to be axial or equatorial, that methyl.
Wait, carbon is gonna be.
So I just made a choice. I just arbitrarily chose to draw it this way. So this methyl right here, do you want to make it up or... I like to make it up. Right? So at carbon 2, what position is up? Axial or equatorial? Equatorial is, right? So let's make this one has to be an H, and that's a CH3. Good? So now carbon 3, right, it has a axial up and an equatorial down. So where should that chlorine be at? Should it be equatorial or axial? It has to be equatorial, right? Because we know, right, it has to be opposite the CH3. So the chlorine's equatorial and this H is axial. Now carbon 4. We have down axial, up equatorial. Where do you want to put the ethyl? Is it going to be axial or equatorial? Equatorial, good. And so this is an H. Carbon 5, we have up axial, down equatorial, but carbon 5 just has H's. Now carbon 6, we have down axial and up equatorial. So where do you want to put the bromine? Axial or equatorial on carbon 6? Equatorial. Good. So then I fill in an H here. Right. You should be able to go back and forth between these two. Right, between these two. There is another conformation I could have drawn here though, right? I could do a ring flip as well. Or I could have drawn the other isomer of the chair. Do you see that? So let me do a ring flip and show you what it's going to look like. But is everybody clear on, right, why are things axial and equatorial? Yep.
The two middle carbons, I get confused on positioning of, like, what is it, 6 and 3?
6 and 3?
Yeah.
So so if I start at carbon 1, right, and you know that's axial up, then this other one has to be equatorial down.
Okay.
Then go over to carbon 6, and it has to be just the opposite. Right? You can't have two axials up ever next to each other. Right? It always goes every other one. Yeah, those ones are the tricky ones. And the other hard part is which way to push to the equatorial. But the way to figure that out is, right, if you divided the molecule in half, right here, right, you notice carbon 3 is on the left side. So have the equatorial go to the left. Right? See if you split it down the middle here? Then carbon 6 is on the right side. So have its equatorial go to the right. Yep.
How do you know which to start at? So, like,
I just made it up.
well, yeah, but, like, if I started on carbon 1 over there.
This carbon one?
Yep.
Yep. You could have made this carbon 2.
Okay.
It's arbitrary. So I totally made it arbitrary, yeah.
Okay, and how would you decide, so like if you looked at carbon 6 on that also, how would you decide that the BR would be an equatorial?
Good.
And not axial?
So then I go back to this, and I see the BR and the methyl are both going up, right?
So if they're
So-
going at you, then they're going up?
Well, that's the easiest way to think about it. That's the way I think about it. But if you notice right how I drew it, see the CH3 here is going up? So that means the BR must also be going up to match this.
Okay, so what if I drew it up? If I drew it opposite, would that still?
Then the BR would be hatched.
As long as they're all.
That'll be different.
Well, like if I drew all of them opposite.
So then let's do the ring flip then, right? So let's do the ring flip. Are you ready?
Yep.
So the ring flip Essentially, that means is I'm taking carbon 1 and pulling it down, and taking carbon 4 and pulling it up. So you got to draw the opposite chair conformation, which I'm not as good at drawing either. Not my best one either. I always go to that one. Let's see if I can do it now. All right. So now this is 1, 2, 3, 4, 5, 6. So the fact that bromine was up never changes, right? Whether bromine's axial or equatorial, it always has to be up, right? So on carbon 1, right, so when you do a ring flip, everything that was axial becomes equatorial, and everything that was equatorial becomes axial. But whether it's facing up or down, does that ever change? No, you can't change that, right? If the bromine's pointed up, it's pointed up, right? That's why that first question I asked you, right? Axial can be up or down. Equatorial can be up or down, right? So if bromine's up, it is up. Right? The question is whether it's axial or equatorial. That's the question, right? So if you look at carbon 1, right? So that's not a good one to look at, but look at carbon 2. So carbon 2 had a CH3, right? If we look at this carbon 2 right here, and that CH3 was up or down? Up. And it was equatorial or axial here? So in this one, it's going to have to be an up. So it's up, CH3. And the other guy is axial, down. So now carbon 3 has a chlorine. What position is the chlorine going to be? Axial or equatorial? It's going to be axial down. Now 4, that ethyl is going to be axial or equatorial? It's going to be axial. And 5, don't worry about. There's nothing really on 5. Now 6, what's on 6? 6 is a bromine. That bromine's up or down? Up, so it's going to be axial. It's kind of in the way here. And then the H is there. So now a lot of things are axial, right? Now? So which conformation do you think is more stable? If I call this one A, and I call this one B, which one do you think is going to be more stable? Which one? A, why? Would you rather have things axial or equatorial? Right, that way, right, in axial conformations, things can essentially bump into each other, right? Look how they're all sticking up in the plane. Right, so everything equatorial is always going to be better. All right, an acid-base question. I guess I'll do this. I'll use 3 molecules. I'll use this guy. This one. And that. 3 molecules. So let's take a second and figure out what they are. Okay, so looking at these 3 molecules, let's label them A, B, and C. We're essentially looking at here in all these cases, right, the acidity, right, the weakness or the reactivity of this OH bond, that OH bond, and that OH bond, right? OH bonds by themselves are essentially the same strength. But the biggest thing here with all of these is going to be stability of products as well as induction pulling on this bond. So this should look familiar to you, very similar to H2SO4, right? So this is a really strong acid, right? So this would be my, if I had to rank these according to acidity, this is 1. Then of course B is what kind of functional group does that represent? B? Carboxylic acid, so that's of course 2. And then this would be 3. Now, you want to separate all of these. Right? So ideally, I would tell you something about the pKa, right? Because you could then say, I need this exact pH to get 100% of this deprotonate. But we're not gonna go there just yet. Just qualitatively thinking about this. If we took all 3 of these things, right? And we put them in a SEP funnel. We have 2 layers. Let's say the top layer is the organic layer. What pH do we want the bottom water layer to be? To get just one of these. So these are all what? All these are what? Acids or bases? They're all acids. So what pH do I need to get just one of these deprotonated? Slightly basic, we'll say. Let's say 8. Really, I mean, that's probably even overkill. Let's just say 8. So, right, and now this is not exact. Like somewhere somebody's going crazy about in Gen Chem about what I'm doing right now. But we'll you know, whatever. pH 8 is basic, right? So which compound is going to be in the water layer? A, B, or C now? Which compound, if my pH is 8 and I shake this up, C should be in the aqueous layer, right? That's the strongest acid, slightly basic, that's going to be deprotonated, going to be charged, going to be the water layer. So now C goes here, and A and B are still in the organic layer. Good? So now you're going to have a beaker with C. If you want to get C to come back out, you need to reprotonate, so make it acidic, right? So pH 7. That gets you C. You can filter it away. In a new SEP funnel, right, you're going to take these guys and put them in. And I got 2 new layers. This, of course, is still your organic layer. What pH should I make this layer now? Now I have A and B left over. What pH should I make this? Let's say 9. Right? So now what's going to be in the aqueous layer now? B should be, right? And then C should be A will be by itself. So B, you got to do the whole reprotonation deal. All right, pH equals 7. That'll give you B. And then A, you need to rotovap, right, to get your final product. Right, so that's how you can separate 3 acids from each other, just by controlling the pH, right? And obviously I know there's a right way, an exact way you can do the math and do this, which we'll probably get to eventually, but we have to actually see what we're doing here, right? Think about what we're doing here, right? Hopefully make this make more sense. Let's do an acid-base reaction with things that you sometimes consider probably both to be acids. So now you have a carboxylic acid and HCl, right? So, acid-base reaction is just the same as any other reaction we've done, a nucleophile and electrophile. Somebody has electrons, somebody wants electrons, right? What is the weakest bond? What's the electrophile in this reaction? You have 2 choices. So so the question is, where's my weakest bond? The weakest bond is it OH or HCl?
HCl.
Chlorine's bigger, right?
Yeah.
It's gonna be less orbital overlap. The HCl bond is definitely weaker, right? So that carboxylic acid is actually gonna act like a base, because, right? First of all, you should know this, right? HCl is one of the strong acids, so it's fully reacts, right? It's super reactive, right? So even though this is carboxylic acid, it's gonna react like a base, because this is such a good acid that, right, if I showed you pKa's and said, right, pKa equals 3, and I said pKa equals -5, right, somebody's got to be the base, and that somebody this time is actually the carboxylic acid. Oops, wrong way. Right? I know it looks weird, right? But what's your best electrophile? Right? HCl is the best electrophile in this case. So carboxylic acid actually acts like a base. All right, let's look at some mass spec type stuff, right? Where we take a molecule, bombard it with electrons, an electron beam, we knock an electron out, and we watch it fragment into those positively charged fragments. So let's take this ketone, for instance. I like to draw in the lone pairs. You always should, even though if we don't draw them in for you. So this poor guy is getting pulled into the electron beam. Right? What's the easiest electron to knock out? Is it in a bond, or would it be in a lone pair, you think? Lone pair, right? There's there. So let's knock that electron out. Right? That'll give us this molecule where there's a plus now. Right? We call this the molecular ion. Right? That's the maximum mass you'd see in the mass spec. Remember, we only see positively charged things, right? Because the electron essentially doesn't weigh that much, so that doesn't really affect the mass that much. So that's the molecular ion. That's not necessarily the base peak. The base peak is the most abundant, stable fragment. Usually the molecular ions are not the most stable thing, because usually once you lose an electron, you want to start breaking up in fragments to something more stable. It's kind of like rearranging a carbocation that we know now. So, let's do the alpha cleavage, the heterolytic cleavage. So that one, we draw 2 electrons in, right, between the alpha and the beta positions. This is alpha. This right alpha means it's right attached to the plus charge thing. This is the beta. So to do this alpha cleavage, so I'm going to show you this alpha cleavage. Essentially, these electrons. One electron is going to go to this beta carbon, and the other electron is going to meet up right there to form a new pi bond. So this is the alpha cleavage. All right, we're moving one electron at a time, so we call it homolytic. New pi bond. Plus charge is still there. And now we have the other electron is here. So the part we actually see, right, is only the positively charged fragment. That's the actual part we see here in this case.